So I said, if you have the shear force diagram, right, whatever that is, this section will give you tau as a function of V, right? So it'll tell you the shear stress. And once you know the shear stress, then again, that will be feed into your mode circle, because one of the components of the mode circle is the shear stress. Then that is used in mode circle. Of course, you also need the normal stress, and the normal stress is something which you already did. So that's the whole idea behind this section. Get the shear stress from the shear force. Okay, so a bit of derivation. So I'm putting some random loading on a beam. Okay, and what we do is just like the previous section, we choose a small element of the beam and then blow it up. Okay, so let's call this face C prime D prime, the right face as CD. Okay, and let's assume that this section is at a distance of y1 from the neutral axis. Okay, and also let's assume that the distance of the outer, well, yeah, let's call that C as the distance of the outermost part. So it's D prime. D prime D is at a distance of C from the neutral axis. Okay, I need to draw the side view also here. So the side view of this beam. So if this is X, this is going to be Y and Z. And then when I draw the side view, which is just below the side view near the beam, I would have this distance again is Y. And then let's say that this width is denoted by B, and that's in cross-section area dA. Okay, so with that, we are sort of ready to start deriving an expression for the shear stress. So first of all, what a shear force does is it basically causes the one plane to slide against the other, right? Now, that shear stress cannot exist by itself. There's a complementary stress which is produced at the other surface. What I mean by that is, if there's a beam, like so, there's a shear stress. So this is along the X. This shear stress on this face will produce a shear stress below, right? Which will be complementary. That's what we derived in the previous few sections back. The shear stress is complementary. So let's assume that the shear stress induces a force. Let's say that it is delta H along the horizontal direction. It is induced because of this shearing, as shown on this figure. There's also going to be a normal stress. Since that element has got a finite width, this face is going to have stress sigma 1, and this face on the right side has going to have sigma 2, and they're different. So now what we can do is we can do equilibrium about the forces in the x direction, where x is this direction as shown. So then we have delta H, which is acting to the right. So let's say that's positive. There's sigma 1, which is also acting to the right. And since it's acted upon by this across this cross section, dA, the force induced by sigma 1 is sigma 1 times dA. So stress times force, sorry, area gives us the force. And then sigma 2 is going to be negative because it's acting in the other direction. So the net force is 0. So we can write delta H as sigma 2 minus sigma 1 times dA. But we know that sigma equals my divided by I. This is section 310. So we can write m2 y divided by I minus m1 y divided by I times dA. So I can pluck out y and I as a common factor. So we have delta H equals y divided by I, right? The moments first, m2 minus m1 y divided by I times dA. Okay, so what's going on here is there's delta H, which I wrote down. So in that phase, so I'm going to draw like a 3D view of this one. So delta H is acting here. And this is, let's say this is dx, length dx. And then we saw the width is b. This is dx. So the stress is, this is the shear stress due to the shear force delta H is simply delta H b times dx. Sorry, my bad. Delta H is stress times the cross-sectional area, b times dx. Okay, so now I can write from 1 and 2 tau b dx. Okay, I'm going to sub in m2 minus m1 as the change in moment from face left, from the left to right face. So dm yi dA. Okay, yeah, there's a piece missing here. Should have done this. So this is actually the total force, and I should have put the total force, which is the integral of this, the integral of that. And so then I need to equate H and not delta H. There's an integral here. So tau equals dm dx times 1 divided by b integral y times I dA. But dm dx is nothing but the shear force from calculus. Give me a minute, I'm almost there. I'm out of time. Tau equals v divided by this I is actually independent of the integral y dA. So we have v divided by I times b integral y dA. Now, when you take this integral, you're basically taking this integral from y1 to c, where y1 was something I drew earlier. y1 is this face, the bottom face, you go all the way up to the height of the block. So this integral sometimes is written as q, where q is called the section modulus. No, it's not a section modulus. It's called, I'm blanking on what it's called. I'll fill in the details next time. But the equation for the shear stress is VQ divided by I times B, where Q is the integral of y dA from y1 to C. So I'll continue next time, but this is the key formula. Well, once again, what the shear stress is if you have a section, I mean a small element, and you need to look at the bottom face. So something like this. So that's the top, that's the bottom, and that's where the shear force acts. So this is assuming there's like a small element of the beam as I showed earlier, and then this is, say, the neutral axis. Then this bottom section is at a distance of y1. The top section is at a distance c. Okay, we used a different notation earlier. I think we use y max for c. Okay, so now let's try to see this formula and see where shear stresses are maximum, where they're minimum, because that's kind of important for design. So tau is max. Okay, it's going to be max when the term here is maximum. B is constant, assuming the width is constant. I, the inertia, is constant. The shear force is given at that point, so that's also a constant. The only thing which determines max or minimum here is Q, okay, which is this in term y dA. Okay, so tau is max when integral y dA is max, and that will be max when y1 equal to 0. That is, it be in the middle of the section, right? When this is y1 equals 0. In other words, the shear forces at the maximum at the neutral axis. And then tau is minimum when integral y dA is minimum, and that occurs when y1 equals c. In fact, y dA is actually equal to 0. So the shear force at the top section is actually going to be 0. So because of the formula VQ divided by IB, the way it is, you will see that different cross sections would have different shear forces for a given with the same V, depending on Q, I, and B. Okay, so let's talk about tau for a rectangular cross section, because that's usually the most common section used in design of beams. So I've again drawn a small element, the one I showed earlier. Okay, and let's assume that the width, this thing here, is B. The bottom section is at a distance of y1. The top section is a distance of c. And then this and there's a small strip here. Let's say that is dy. Okay, and that strip dy is at a distance of y from the neutral axis. Okay, so now we're in a position to find the shear stress, okay, which is given here, VQ divided by IB. Turns out that V is as I said, is fixed for that section. I and B are fixed. So only we need to figure out what Q is. Once you have Q, let's put it in the formula and find a formula for the shear stress. So Q equals integral y1 c y dA, where y I've shown there. Now dA is this cross-sectional area. So it's going to be b times dy. That's the cross-sectional area of this thin element, this dy. And then if you integrate that, you get b, which comes out y1 c b, sorry, y dy. And then the integral is essentially y squared divided by 2. Upper limit is c, lower limit is y1. So we have b c square minus y square, y1 square. Okay, so the formula for tau is now vq divided by I times p, and that can be written as v divided by I, and q is b divided by 2, so that b and in the numerator cancels the one in the denominator, and so we get something like this. Okay, I'll do a little bit more simplification and bring this expression down to fewer variables. Okay, so that's what I had. Now, if we think of a beam with, say, okay, again, the width is b, but let's say that the height is h. So this is basically an element of a beam, which is essentially something like this. Right, that's the whole beam, but then I just took a section when I showed it here. So what we see is, well, C is this. So this is H. And this is C. This is the topmost part of the beam. And so what we can do is we can try to write expressions for inertia. So if I write that 2C equals H, okay, that's just the notation I used. The inertia is, we know that the inertia is 1/12 B times H cubed, but H is 2 times C. So 2C cubed. And so simplifying this gives me 2 divided by 3BC cubed. Okay, so take this formula, sub the values. V divided by 2, the I is 2/3 BC cubed, and then C square minus Y1 square. Okay, we can do a little bit of more simplification. The area of cross section is B, as you can see, times 2C, or B times H, but H is 2C. So B times 2C. And then this formula further reduces to tau equals V divided by, sorry, 3V divided by 2A. A is the cross-section area, 1 minus Y1 square C square. Okay, so that is the formula for the shear stress in a rectangular beam as a function of the distance Y1 which is the distance from the neutral axis. So now it's easy to see that the cross-section area is the same, it doesn't change, right? V is given, so it attains a maximum value when y1 is 0, right? Because there's a negative there. So anything other than 0 will give a lower value of tau than it is with a 0. So tau equals 3V. Now, if you go ahead and plot this, so this is a beam. That's the neutral axis. Okay. First thing to note is that the shear stress is maximum at the center. So let's say that this is the shear stress. Tau max equals 3V divided by 2A. And then it's 0 at the edges, right? Because when you put y1 equals c, you see that we get 1 minus 1, so it's 0. So it's 0 here and 0 there. And between those points, if you want to connect, you want to use this equation to connect. And that equation is the equation of a parabola. So it won't be a straight line. So it will actually be this way. So this is actually kind of interesting. If you take what we did here in this section with what we did in the previous section about moments. So when we looked at moments, okay, so for moments, we said the sigma, the normal stress is my divided by A. And for shear stress, it's 3V divided by 2A, 1 minus y1 square divided by c square. If you plot that's the beam. If you plot the moment, the normal stress, it'll achieve a maximum value when y is maximum, and it'll decrease linearly. This is y equals 0. If you plot the transverse or the shear stress, you'll see that it is something like this, with the maximum value here at y equals 0. So here sigma equals 0, and then sigma equals m y max divided by I, and same over here with a negative sign, but the shear stress here is 0. So the shear stress achieves a maximum value at the center, but the normal stress is 0 there. And then the shear stress at the edges is 0. However, the normal stress achieves a maximum value. So what you notice is that if things are going to fail, they'll fail either at the surface due to normal stress or moment, or they will fail at the middle section due to shear stress. Make a note of this. Achieves max at the surface and is 0 at y equals 0, which is the neutral axis. Tau, on the other hand, achieves max at y equals 0, which is the neutral axis, and is 0 at the surface. So this kind of concept is kind of important when you are going to design, right? If you're given two competing theories of failure, you will check the maximum shear stress at the surface, and you check the maximum normal stress at the surface and shear stress at the neutral axis. Now, there is a table in the book on shear stresses for different geometries. I'll just put it here. It's the one. Okay, it's taken straight from the book. Okay, it basically gives you shear stresses for different geometries. So we've seen one for the rectangle. It's on the top left. Then there are two more sections which are circular on the top right and bottom left, right? Circular section and an annulus. In all cases, you can see that the shear stress achieves a maximum value at the neutral axis, and it's 0 at the edges. Okay, it's kind of interesting for the I-beam. You can see it's almost maximum sort of till here. At all this, you have almost similar stress, and then it just goes to 0 at the edges. So you see that there's sort of a disadvantage of having an I-beam, because when it comes to shear stress, because the shear stress is kind of high at the complete the vertical part of the I-beam. And then you can obviously do these things for the moment, and that's where a design problem happens, right? When you have two competing stresses, which stress dominates, and whichever stress dominates is the one which you'll be using to design. So that's a question which will come today in another question.